Hello, I'm Derek Poyer. I'm with 3M's Corporate Research Analytical Lab where I do XPS analysis. I previously worked in the contract analytical labs of Physical Electronics and Evans Analytical Group. I want to thank my friends at PHI for the opportunity to present at the virtual fall workshop. I hope that this presentation on preventing Lab 6 deactivation will be interesting and helpful to other PHI XPS users. A quick summary of 3M. We are a global company with about 30 billion in annual sales. We're arranged in 4 business groups, which I'll introduce on the next slide. We have 93,000 employees globally. We pride ourselves as being innovative, as evidenced by our 117,000 patents and counting. And we also take pride in being a steady performer with a streak of over 100 years of paying dividends to shareholders. 3M is one of the companies included in the Dow Jones Industrial Average. We're currently organized into 4 business groups: safety and industrial, transportation and electronics, healthcare, and consumer. Now, each of these business groups includes multiple divisions which produce our wide variety of products. A small sampling of the products coming from each business group are shown here. At one point, 3M had 55,000 SKUs, so clearly only a small sampling is possible. 3M's earliest products included sandpaper and masking tape, and abrasives and adhesives remain staples of our portfolio. Our safety and industrial group produces things like grinding pads, painting systems for automotive repair, N95 respirators, which you may have recently become aware of in the age of COVID-19, products for hearing protection, VHB tapes, which may be holding parts of your car together, roofing granules for shingles, and electrical tape. In transportation and electronics, they make things like vehicle wrap film. They make many types of films that improve the function of electronic displays and also privacy filters for displays. They make retroreflective safety films. And they also make cleaning products such as the Scotch-Brite pads for industrial floor scrubbers shown here. Our healthcare group has a leading line of stethoscopes and also makes things like Coban wraps, a wide variety of medical tapes, clear tray aligners for orthodontia, Tegaderm products including securement devices for IVs, and water purification systems. You might recognize a lot of the products over on the right side, which are directly marketed to consumers. These include things like Post-it notes, Filtrete furnace filters, command strips, Scotch magic tape, and blue painter's tape. So part of the excitement and the challenge of being a surface analyst at 3M is the variety of products and materials that we're asked to analyze. Where does the analytical lab fit into 3M? Well, in addition to the 4 business groups from where products flow, 3M has a group of corporate research labs that interact with all the business groups. These include the analytical lab, which I'm a part of, that leads in measurement technologies for the company. Also included is the materials lab that is tasked with developing next generation adhesives, abrasives, polymers, ceramics, and other materials. The process lab develops new technologies to enable manufacturing of new products. And the systems lab develops software solutions and integrates data analytics and artificial intelligence into our information systems. In Corporate Research Analytical, we currently have 5 physical electronics surface analysis instruments, including the Quanterra, VersaProbe, and Nanotop instruments in our St. Paul lab. We also have a VersaProbe and Nanotop instrument in our CRAL lab in Japan. We also use instruments from other manufacturers, and this has allowed us to really appreciate some of the things that PHI instruments excel at. For example, our Quanterra is unmatched for high throughput analysis, and this is due to the ability to have multiple sample holders in the instrument, the ease of setup for repetitive measurements in SmartSoft, and the superb automation. Also, after trying other systems, I can offer the highest praise to PHI's SXI imaging system for locating small features for analysis. This is really the fastest and easiest system I've come across. Of course, at the heart of PHI's microfocused X-ray source that allows SXI imaging is the lanthanum hexaboride or Lab 6 emitter, which has provided us some challenges at 3M with deactivation, as I'll describe further. So I'll lead into that discussion with an example of the type of analysis that's often requested of us at 3M. The product in question is a foam tape that is used as a ring tape in mobile phone construction. It's been specifically engineered to provide appropriate damping to lower the chance of screen breaking when a phone is dropped. In this analysis example, 3M received a complaint from a phone assembler that the ring tape adhesion was too low. The usual suspect in cases like this is silicone residue on the adhesive that has been transferred from the release liner. So here's an image of the roll of foam tape as produced. It's wound up on a two-sided silicone release liner. In the center is a cartoon of the converted product produced by a third-party converter that die cuts the ring shape and then swaps release liners. Now, release liner science is more involved than you might think. In order to unwind this roll of foam tape from the double-sided liner, the silicone on the outside of the roll must release the tape while it remains firmly bonded to the opposite liner surface. It also needs to stay well attached strongly enough for the converter to cut it and remove excess material. Then the converter applies liners appropriate for the assembler, who needs an easy liner that comes off first and a tight liner that will come off last in order to properly apply the tape into the assembly. In order to achieve appropriate peel strength from liners, properties such as silicone chemistry, additives, molecular weight, and thickness are varied. If something isn't done correctly, too much silicone remains on the adhesive, and that is what we were asked to check for in this particular example. So shown here are XPS data from both sides of retained foam tape and from both sides of converted tape. Surveys are shown on the left. XPS surface percent silicon is shown in the graph in the center, and the high resolution silicon 2P is shown on the right. From the bar graph, we can see that there is silicon on all the surfaces, and this is not surprising. Rather, it's not the presence of silicon that we're looking for, but the level that we're trying to determine. The as-produced foam tape had about 4 to 6% silicon, which is known to be an acceptable level. But we see a much higher value on the backside of the die cut. We also notice that the silicon chemistry on the backside of the die cut is quite different from the silicon on the other surfaces. The other surfaces have a single silicon 2P feature that's consistent with PDMS silicone. The backside adhesive, however, has a different signature that includes silicon 2P at higher and lower binding energies. This is a signature of a silicone additive known as MQ resin, which is often added to increase the release force of a liner, that is to make the release tighter. The notation for the different forms of silicon present refers to the number of oxygen atoms bonded to the silicon atom. So in PDMS silicone, all the silicon atoms have 2 oxygen neighbors, and these silicon atoms are referred to as D units. MQ resin is a silicon oxygen methyl group network with a silica-like core, where the silicon atoms have 4 nearest neighbor oxygens and are referred to as Q units. The silicon atoms on the periphery are bonded to 1 oxygen and 3 methyl groups and are referred to as M units. What we see in this example is that there's excessive silicone transfer in the form of MQ resin on the backside of this converted ring tape. So this signals a problem with the tight liner that the converter was using. So hopefully I've shown you an example of something that XPS can do that's useful for our engineers at 3M. What I didn't mention yet was that when this foam tape is introduced into the XPS instrument, it causes Lab 6 deactivation, and carrying out this experiment actually requires some ingenuity. So for the rest of the talk, I want to talk about how a sample that causes deactivation of the Lab 6 emitter in the XPS instrument can be successfully analyzed by including a second sample, such as a 3M Post-it note. So in normal operation of the XPS system, the Lab 6 emitter is a point source of electrons for the microfocused X-ray source. If all is well, a healthy beam of electrons leaves the emitter, creates a strong beam of X-rays that's focused onto the sample, and we get good photoelectron signal. But occasionally, a sample will cause a problem with the Lab 6, perhaps just causing it to run at a higher temperature to maintain emission, but possibly also resulting in a loss of electron emission, and subsequently a weaker X-ray beam and reduced photoelectron counts. It seems in these cases that something is being emitted by the sample that's causing a problem, but what is it, and what's the nature of the problem? Well, I believe other possibilities exist. I think the issue we typically face at 3M is that there are volatile organic species coming out of the sample. These might be additives like tackifiers in adhesive, or they might be retained solvent or unreacted monomers that sublime into the vacuum. As these volatile organic compounds start to make up a part of the residual gases in the vacuum, some will find themselves in the vicinity of the electron gun, where they can be excited, ionized, fragmented, and begin to build up a carbonaceous layer on the surface of the Lab 6 emitter. Now, a priori, you might expect that deactivation could be related to oxidation or other types of poisoning. As it turns out, Lab 6 deactivation has been studied for some time. I thought it was interesting that it was generally in the context of ion propulsion systems for satellites and spacecraft. Apparently, this is a thoroughly explored material for electron impact ionization of gas atoms that can then be electrostatically expelled to provide thrust. The reference shown here I found to be particularly enlightening. What the authors suggest is that oxidation of Lab 6 is not likely under the low pressure and high temperature conditions of Lab 6 operation in XPS. But carbon poisoning is likely if carbonaceous species are present in the atmosphere. Interestingly, the authors also noted that carbon poisoning could be mitigated to some extent by the presence of CO2, which suggests that adding a source of oxygen to the vacuum could reverse the carbon poisoning. At this point, I just want to point out that Lab 6 poisoning has long been known to PHI, and that they've included O2 lecture bottles on their XPS instruments and procedures for reactivating a Lab 6 by admitting a low level of oxygen into the system. I've used this procedure many times, but I've also had many times that I needed to get some data for one emergency or another, and stopping an experiment multiple times to do O2 reactivation was not possible. That need led to the following procedure. So on the left, we have our off-gassing sample causing poisoning of the Lab 6. And on the right is an alternate experiment where we've included, along with the off-gassing sample, a portion of a Post-it note. With this extra sample present, no deactivation of the Lab 6 is observed. And we've used this trick many times to get data from challenging samples. My theory of why it has worked is that water is gradually emitted from the Post-it note, which provides a source of oxygen that can remove any carbon poisoning before it has affected Lab 6 emission. So I'd like to share with you some data that I think proves out this hypothesis. What we need to monitor to see evidence of Lab 6 deactivation are the emission current, which is of course the electrons coming out the end of the Lab 6 to produce the X-rays, and the filament current, which is basically the heater current controlling the Lab 6 temperature by way of a feedback loop. If emission current starts to fall, heater current is automatically increased to bring it back up. So we can see deactivation as increasing heater current in a mild case and falling emission current if the control loop hits the filament current limit in a more severe case. I'm going to show you how heater and emission current varied during two experiments as described here. In experiment A, I'll show the data in red. The X-ray source was operated to show stability, and then platen 1, containing an off-gassing sample, was moved into the chamber. After evidence of deactivation was observed, a second platen, containing a portion of a Post-it note, was also moved into the chamber, and reactivation of the Lab 6 was observed. In experiment B, the data will be shown in blue, the off-gassing sample and the Post-it were inserted on one platen, and no deactivation of the Lab 6 was observed. So in the plot in the upper right, we show that our filament and emission current during the two experiments, and in the lower plot, we show the pressure during the experiments. So considering the red data first, you see the X-ray source initially operating in a stable manner until the point that the tape sample was introduced into the chamber. At that point, you can see the filament current begin to rise. So this is a mild case of deactivation, since the emission current has been held constant throughout. I also want to point out that the system pressure with the tape present was not excessive, and in fact very typical for the types of samples we routinely analyze. So this deactivation is not the result of a recklessly high pressure, but seems to be due to some particular species that off-gasses at a very low partial pressure. So after demonstrating this deactivation, the Post-it note was introduced, and here you can see that the filament current quickly dropped back to the original level. There was a brief spike in the emission current since the control circuit could not react instantaneously to the reactivation that occurred when the Post-it was introduced. Note here that introducing the Post-it did cause a significant increase in the pressure, yet resulted in improvement of the Lab 6 function. Data for the second experiment, where the tape and Post-it were introduced together are shown in blue and are pretty boring. There basically is no perturbation of the emission or filament currents when the tape and Post-it are introduced at the same time. When we first developed this approach and started using it at 3M, I was very excited to share it with my friends at Phi. I had also been in discussion with them about whether a cerium hexaboride emitter might be less prone to deactivation. I'm very grateful to David Valley at Phi, who did this similar experiment with the same 3M tape and Post-it that answered several additional questions. First, David did the experiment with a cerium hexaboride emitter. And second, he used an RGA to track the gases present in the system during the various stages. David's data shown here for inserting tape alone showed that the cerium hexaboride did indeed deactivate. And in this case, the deactivation reached the limit of the heater current, which resulted in the loss of some emission current. So this is a more drastic deactivation that occurred. While the tape was in the chamber, David saw an increase in H2O partial pressure. He saw spiky N2CO and O2 pressure while the foam tape was in the chamber. My speculation on that spiky nature is that it may reflect gases irregularly escaping from the cells of the foam structure. But with a more gradual and smooth buildup, he saw the increase of various hydrocarbon partial pressures while the tape was in the chamber. The mass 55 result is plotted here in purple. This is in agreement with the hypothesis that the tape emits a series of small organic molecules that lead to carbon poisoning. When the tape sample was removed from the system, pressures came back down and the cerium hexaboride gradually regained its original level of emission. When David repeated this experiment with some pieces of Post-it note also on the sample holder, the emission and filament currents were essentially constant. The same hydrocarbon partial pressure was present, but the water concentration increased by a factor of about 20 times than it had been without the Post-it notes. So this supports the hypothesis that H2O is the beneficial species that's preventing the deactivation. So some of the conclusions here. We see that both lanthanum hexaboride and cerium hexaboride emitters can be poisoned by off-gassing from certain samples. So far, it's unclear if one is better than the other from what we've done. Offending species, at least in the case of the samples that we routinely look at 3M, include organics that seem to result in carbon buildup on the Lab 6. These can come from retained solvents, adhesive tackifiers, and unreacted monomers in the samples. We've shown that the carbon buildup can be reversed or even prevented by adding H2O partial pressure to the system. In our case, we used a Post-it note to show this. So anticipating some possible questions. Does it have to be a Post-it note? And the answer is absolutely not. It could be any piece of paper or any material that slowly gives off water in vacuum. Just use the Post-it note as an example of a 3M solution to a 3M problem. I also just want to point out that the adhesive on the Post-it note has nothing to do with what's going on here. And we usually don't include the sticky part. We just cut a portion of the paper without adhesive. Now, before we realized this, we tried many other ways of overcoming the deactivation. So an obvious one is to reduce the VOC load. So cutting smaller samples, loading fewer samples at once, pumping longer are all possibilities that can potentially get you through an experiment without the deactivation. Another thing we've done is to just adjust the X-ray setting so that it runs at lower emission current so that the control circuit can keep up with the heater. We've also tried just opening the gate valve to the intro, which causes a small boost in the analysis chamber pressure. And this is often enough to ward off the deactivation. On our VersaProbe, we happen to have a manual leak valve that's used to introduce oxygen for reactivation of the Lab 6. And since that's available, we can actually introduce a very low partial pressure during the analysis and ward off the deactivation in that way. Are there negative effects of including a water source along with the samples? And I can say that we have not seen shortened lifetimes for any of our components. In fact, during the period that we've been Doing this, we've had record lifetimes for several of the filaments that we've had in our system, going on the order of 2 years without having to open the vacuum chamber. One thing that we have noticed is if you have used water to prevent deactivation for some period of time, the barium oxide flood gun can take a longer time to reach its emission set point on startup. Sometimes we'll get a warning sign, tell the, or a warning in the software, and just tell the software to try again, and it's usually taken care of on the first try. So if this works for a while, could you conceivably extend the Lab 6 life indefinitely? And this does not seem to be the case. Experience has shown that as you observe deactivation with the Lab 6, it seems to be easier and easier as the filament ages. And looking again to the literature, it's been suggested that the effect is that the 110 facet of lanthanum hexaboride is the most efficient emitter, but that a hot crystal can evaporate some material and you'll start to form 111 facets, which are less efficient at emitting. So this may be what decreases the efficiency of the Lab 6 over time. It also suggests that it's a good idea to monitor your filament current, and if you do see instances of the current rising, minimize any overheating events to prolong the life of the Lab 6. And in terms of, might the cerium hexaboride emitter give a longer life, we don't have any evidence so far from this work, but product literature suggests that the cerium hexaboride has a lower evaporation rate at operating temperature. So the faceting effect that has been attributed to the deactivation of lanthanum hexaboride might be slower and might have an improved lifetime. With that, I'd like to thank you for your attention and take any questions. Thank you.